Alright guys, welcome back to another segment of GGTutoring. Today's episode is going to focus on epoxide synthesis. So most of you guys probably got the final exam coming up soon, so hopefully this is some good review for you guys because it's time to lock in and get that A. So basically an epoxide is just a ring with oxygen. There's like different ways you can draw it, but really the main thing is just like this basic structure on the left. So there's different ways to synthesize these epoxides. There's a halohydride synthesis and there's the peroxyacid synthesis. The halohydride synthesis takes a bit longer. It's like more steps in comparison to the peroxyacid synthesis, but there's different ways to achieve an epoxide, and the assessments might cover both of them. This BR2 is basically just an X2 addition. It's what I've covered in a previous episode. It's the same concept. So basically you have like this BR2, and because it's approaching this double bond, one of them is polarized and becomes a partial positive and one's a partial negative. So then the electrons in the pi bond are going to come to this bromine, and then one of the lone pairs on the bromine is going to come back and make a ring, and that knocks off the bromine. And then you'll get a structure that looks like this. So now you have a bromine ion floating around, and you have water as a solvent. The water is going to outcompete the bromine and be a better nucleophile in this case because the hydrogen bonding it's capable of can stabilize the bromine ion, anion, and make it harder for it to actually like outcompete the water solvent. So water typically will add to the more substituted carbon in this case, but I mean in this example they're the same substitutions on the carbon, so it doesn't really matter where you add it to. So the water is going to come in to this carbon and displace one of the bromine, break one of the bonds, and then it'll form something that looks like this. And remember when you're doing these like reactions that when you have like the water coming in and breaking one of the bonds, it always adds anti, so they'll never be in the same plane as the bromine. So one will always be on a dash, one will always be on a wedge. So just remember that when you're doing that. And then this water that added, it's gonna obviously deprotonate. So now you're left with the OH group. So now that was basically the majority of step 1. So now I'll do step 2, which I'll write in red now. So basically you have this base OH. So what's gonna happen is you have OH. The Na doesn't matter; it's a spectator ion. So you have the OH that comes, and it's gonna take one of the hydrogens off the OH and put it back into that bond. So then you'll get this. And then now what's going to happen is to make an epoxide, this special case of like intramolecular interactions. So this the negative charge is going to come in, form a bond, and then displace that bromine. And then you're going to get a product that looks like this. So now you get these two, and I drew 2 products because it just depends on which way you make the bromine starting off, if it's on a dash or a wedge. So 50-50 chance of making either of these epoxides, and that looks pretty similar to what I've drawn with the basic epoxide. So this definitely took a lot of steps to do, and there is a much easier way, but it's good to be familiar with this halohydride synthesis because when you're doing a halohydride synthesis, there can be intramolecular bonding, like where this O will just go in and make a ring with itself and then knock off the bromine. So it's good to be familiar with that to make an epoxide. But now for peroxyacid syntheses, there's like 2 main reagents that you should be familiar with. It's not important that you know the whole structure, but like on the reaction appendix it won't say MCPBA or MMP. It'll have like these big molecules drawn. So it's good to see the molecule and be able to recognize and know what it is, but you don't really need to know the electron pushing mechanisms behind it because that's more for 345. But basically this is a much easier way to make an epoxide using MCPBA and MMP. So I drew a new molecule and I'll show you an example. So I've redrawn MCPBA, and I'll do the electron pushing mechanism just for you guys to be familiar with it. But it's not important that you know. But it's good. It's definitely a good idea to be familiar with it. So the electron density in this pi bond is going to come to one of these oxygens and donate. And then when that happens, this pi bond is going to donate its electrons to here. And then so between this double bonded O and then this H, so this O and this H, there's a hydrogen bonding going on. But when you're donating the electrons, and this electrons in this pi bond are actually going to come here and form an actual bond. So instead of just having intermolecular hydrogen bonding, an actual bond will be formed, and then the electrons in this final bond will come back and make a ring. What you're gonna end up with is something that looks like this. Most of the time, like, they might ask you to like make an epoxide, but this doesn't really mean anything much. Like nothing. It's not that important. So most of the time there'll be problems where you start with epoxide and you have to make other things, like when you're doing a synthesis problem. So you need to be able to know how to like open up these epoxides and like serve it. I can make it into a good nucleophile and attack other things and like build bigger chains and whatnot. So there are different ways to actually open these epoxides, and that's based off what conditions the epoxide is in. So there's either basic conditions or acidic conditions, and for both basic and acidic, they have anti-only addition of the nucleophile that comes in and breaks open the epoxide. And for basic, it's governed more by sterics. So I've drawn the same two starting material substrates of the epoxide. So for basic, it's governed by sterics. So you can see that this is very sterically hindered over here. So it's not going to want to add to that carbon. It'll instead add to this carbon that I've circled. And then for acidic conditions, it's governed more by charge alignment. So it'll add, so wherever it has the bigger partial positive charge is where it'll add, which would be this carbon. It'll add, so it'll come in attached to this to that carbon. But both of these reactions basically occur by SN2 within the molecule, so it may seem kind of odd at first why you'd add to this more partial positive charge. But just kind of, you really just have to remember that for acidic conditions, it's going to add to the one with that's technically more sterically hindered, and for basic, the one that's less sterically hindered. So I'll start off with the basic conditions. So you're going to have a OET that'll come in, and it's going to add to that carbon and break this bond. So you'll get something that's like this, right? And then basically this oxygen is still negatively charged. You want to get rid of that. So you have your solvent, ethanol. So that's going to be something like this. And then this lone pair of the oxygen is going to come in and take that hydrogen to form an OH group. And now for acidic conditions, basically what this oxygen is going to do instead, so instead of first going to the carbon, this oxygen is going to take a hydrogen from this H2SO4. So it's going to come in, take it. Ethanol now, since it's acidic conditions, it's going to add to the more substituted carbon. So the ethanol, one lone pair on the oxygen, is going to come in and then break that bond. And now this oxygen is already stabilized because it already took a hydrogen earlier. But this one is positively charged now. So since you have more ethanol in as your solvent, just another one's going to come and deprotonate and stabilize this molecule. And that's basically it, guys. So basically, really the key things to take away is like know how to form these epoxides, because there will be questions on just forming an epoxide. But then you also need to be able to think further when you're doing like more like synthesis-based questions. That you need to take this epoxide and form something else. So you have to be able to open up the epoxides. So you need to be able to recognize the reagents like MCPBA is also to make an epoxide. But when you already have an existing epoxide, there's different conditions to to determine where the your nucleophile is going to add, and that can kind of change the outcome of the newly formed molecule you make, of where it adds. So it's good to keep in mind these things, and hope this video is helpful. If you guys have any questions, please feel free to drop them down below, and thank you guys for watching. Good luck on your finals.